like to tell you something about like case which brings our yesterday story closer, a bit closer to reality. Yeah. So that's it. That's the dispersion profiles of a real crystalline resonator. So you can see it's actually a mass. Yeah. So it's not at all what we simulated during these 2 days, because apparently in real life story is way more complex. And probably you already know the answer why this figure looks exactly like this. So, and the answer is avoided mode crossings. Yeah. So in perfect situations, your different modes, they are orthogonal, so they don't crosstalk actually. But in reality, of course, it's not this in this case. Yes. So because of the scattering and on imperfectness of resonator, you can have light transferred from one mode to another mode. And then there is a situation when FSR of this mode, like they are almost the same, so this crosstalk is very effective. So, and what's going on? And you can see it here on the slide on the left. So one mode crossing another, they actually interact. So this is what we call this avoided mode crossing. And it was shown actually that this avoided mode crossing is quite a painful thing actually, and you want to get rid of this. Because, why? Because of course it affects your Soliton state. Yeah? So if your dispersion profile is not perfect, as we learned yesterday, so if we have D2 and nothing else, we have a perfect Soliton which like just propagates. If we slightly modify our dispersion profile, like yesterday we added D3 for example, yeah, or D4, so then your Soliton like start to deviate from ideality, so you get something else. And it was shown that actually it's very hard to generate solitons when you have this kind of dispersion profile, which is like destroyed by modal crossings. Yeah, you want to get rid of this, and in some cases you can, but it will be largely modified. So there is simple, if you just work with like simple couple mode equations, like just consider 2 modes, and so you can derive this simple formula which tells you how this mode is gonna interact. So it's like one mode is supposed to go by this like by this like green line, but they actually go and story changes completely. And this is how your spectrum in experiment can look like when you have a mode crossing in particular space on your dispersion curve. Yes. So here you have effective transfer of photons to another mode. So and from another mode, so you have a crosstalk, and here you have a sort of Lorentzian shape which comes from the modal interaction. And here is more or less how it looks like. So it was done for like complex mode interaction in the toroidal microresonator. You can see during the crosstalk what's going on. So I think the white lines, white arrows show the direction of your magnetic field in this moment. So you actually take this particular part of the dispersion curve and you can see this, what we call a hybridization. So the modes, they're actually getting something in between these 2 modes, and then they separate again. So you can see this evolution well, yeah. And so you can consider, okay, that's a really bad thing, so we don't want to have it. But in real life, everything can be used, and this avoided mode crossings as well, yeah. And particularly, it was a nice suggestion, actually. Okay, in order to make a frequency comp, like with a really large spacing in frequency domain, what do you have to do? What if we have a resonator? Like we have a fabrication facility. So, and we wanted to have like a large spacing comp, like terahertz and more. What are we supposed to do? Yeah, we get a smaller and smaller and smaller ring. But on Monday, we learned that ring can be really small because of the bending losses. Yeah. So you will lose everything. You have large losses, and not only this, it's like it's hard in fabrication terms, and it's really painful. And so what people proposed is actually to generate so-called a soliton crystal. Yeah, so you generate solitons which stand equidistantly inside your resonator, and effectively your FSR, like free spectral range, it changes, yeah? Because now you have another periodicity inside your resonator. So, and apparently your lines, so for example, if you have just one soliton, you get certain FSR, yes, corresponding to your resonator. It's clear. So you have one soliton circulating. There is a period, and 1 over this period gives you your FSR. But now imagine there are two solitons, which are like just one in front of each other. They propagate like this, yeah. So now you're getting twice more frequent there, yeah. So now 3, 4, 5, and this you can control. There is a limiting number, okay. So it doesn't go to infinite, of course, because your soliton has a certain size, and your soliton can interact, collide, and explode. Yeah? So that's how it works. But have you seen this? It's not simple to do. So yesterday from simulations, you remember that sometimes your solitons just trying to go through modulation instability state, they collide, they destroy it, so you never had this perfect case, yeah? And these are spectra. So you can see here on the left, like the orange one, we have a lot of solitons equidistantly spaced, and your FSR effectively changed, yeah? So you can see the spacing is large now. But if one soliton is missing, the story is not as nice already. Yeah? There are 2 or 3, so you can see your comb line is significantly modified, but you want to have a perfect one, of course, because you want to apply your nice comb to, I don't know, some certain application, wherever, LiDAR, we will see later where you can apply this. Yeah. And so, yeah, so this is the concept of perfect soliton crystal. This you just have your spacing increased by, depending on how many solitons inside your resonator. So that's a kind of, I think it's clear story, yes. So you can just many periodical structures, so of course you change your periodicity. Okay, and actually why it's not so easy. So first of all, you have to go through modulation instability, which destroyed many things. Another one thing, as I told you yesterday, we have this phase diagram, actually the stability chart. And yesterday we clicked through it, but if you go with far in power up, so you can see another 2 zones. It is actually a bit more complex than we studied yesterday. And what we call here is special temporal chaos and transient half chaos. So you can actually trigger in this kind of typical dynamics from these states. And once you tune over this state, you destroy everything what's inside your resonator is circulating. So actually, it was quite a bit of challenging to create a soliton crystal for this reason also. And what we found actually happened here. So it's a work by Maxim Karpov. He just published Nature Physics quite recently, so about this. Is we just go and tune first just below these states we want to avoid, right, which is quite logical. Yeah. But what is more important that you have to get an avoided mod crossing in order to preserve this exact spacing, because your avoided mod crossing, how it works, so actually you got a certain flow of photons towards this kind of place where you have avoided mod crossings. So your background is getting modulated, yeah? And solitons, they take these slots in the modulated background and they sit on them. So you can actually control how many solitons are there because of this. Yeah? So it's a really nice effect. And what you can do, now there is a deterministic strategy how to go and just generate soliton crystal, perfect soliton crystal on demand. So you can really apply it to many fields now. Yeah. But what I want to mention more is today that we studied all this time, during all these days, only anomalous dispersion. But of course, you can do solitons, or you can work with normal dispersion as well. And it's actually easier from the fabrication point of view, I guess, to get a micro resonator which has normal dispersion because of the size, actually. So, and I wanted to mention just, so in just nonlinear Schrödinger equation, there is a dark soliton solution. If you're not familiar with this, so what is going on? So you got a background, yeah, and dark soliton is nothing but a dip in this background. Yeah. So there is a phase jump, of course, we can see it here. that's a multi-Soliton solution in dark case. So it's your like defocusing nonlinear Schrödinger, and remarkably, this was studied like right after the nonlinear Schrödinger equation was integrated, almost in the same paper. They were like really good at this time. They wrote a large paper solving everything, finding Soliton solution, and also for dark case as well. So it's really remarkable. And then there were some experiments or observation of dark solitons in optical fiber. But it's found out that actually it's not that simple in the ring resonator to do this. So and why? Because in order to trigger these dynamics we study, you have to get this modulation grow, you know, to this kind of, if you have some noise, as we learned yesterday, this noise can be exponentially amplified, like the comb lines line inside your noise, there is a certain gain profile, and inside this gain profile, your line is going to grow really fast. But this case, it doesn't happen in normal dispersion, actually. So it's really in nonlinear Schrödinger at minimum. So if you have a noise, just CW noise, and you put it in defocusing Schrödinger, it will calm down. So you know there is no modulation instability. It will be just CW, and that's why it's really hard to trigger any dynamics in normal dispersion. Yeah. So you can, but you have to go to extreme values. And actually, so Stephen Cohen, during I think in the end of his thesis or after, he found that it's possible to get normal dispersion in a ring resonator, but for very, very high like pump and detunings. It's really hard to achieve this in real life because it's really large, like high parameters. So what do we do? So what do we do? There are a few solutions. So first solution is like we can modulate our pump. So well, for example, we can use like two lasers close to each other and just get your background modulated artificially like in this way, and your like instability getting there. So you can generate like dark pulses in this case. But also what you're going to get next as a presentation, you can put a modulator inside your ring, and also like phase modulator, and also like modify your background and effectively generate the dark pulses in the normal dispersion resonator. And Sasha will talk about this just after me, so you will learn about this as well. But there is another one, and who can recognize this? Who saw this already? Can you raise your hands? I'm just curious. Yeah, right, so people saw it. It actually was a test file for Python before you come in, so I uploaded two things. So you run your script, and that's what you see in as the output. And apparently the avoided mode crossing story is valid here as well. And here is a way to simulate the avoided mode crossing without getting too complex. So what you do, you see actually dispersion is turned down, so it's normal dispersion. But there is this kind of effect here. So that's how I include the avoided mode crossings without getting to the coupled LLE formalism. So I just take one LLE and I just make a very complex dispersion profile. I have to work in Fourier in order to not get in polynomial expansion of this, in order to just take this and directly give it to the solver. But that's what you get. And if you look to the number where it is, it's if you count how many FSRs from your pump you have your avoided mode crossings. So it's 4. And actually here we have like every fourth comb line only. Yeah? And what it means? It means we get a Soliton crystal. Yeah. And here how the field looks like inside the cavity. So there are 4 structures. And in experiment, you can effectively control the position of your avoided mode crossings. And this is called Vinny type configuration, where you have 2 coupled resonators, and you actually apply a header on top of one, and so you can actually tune it over a certain range, and you can control where the avoided mode crossing happens because they're just coupled, and there is a mode of one resonator crossing another. So you will see this, and you can control this, and depending how many FSRs your avoided mod crossing is far, like from your pump, you can generate different numbers of it's called also platinum, dark solitons inside your crystal. Yeah? So you got like you got two crystals inside, two solitons inside, three, four. It's actually straightforward, yes. And in experiment, you can control this. That's amazing. So you can on demand generate like different FSR combs on one device, and we studied a bit the mechanism, what's behind this. And in nonlinear sharing equation, there is a very particular mechanism in defocusing Schrödinger, which is called the gradient catastrophe, and it's regularized by emergence of dispersive shock waves. Maybe you heard about this. It's a kind of, if you have this kind of problem, if you have a sharp edge in your internal field, it's going to break and has a regularization, because you cannot get infinite gradients in your Schrödinger. You will regularize it by emergence of this kind of oscillating structure. Yeah? And if you have just, you see, it's very close to what we actually would like to have inside the resonator, but it's just a Schrödinger. Okay, so we get some sort of modulation. It's going to be defocused, like there is a defocusing dynamics. They're going to collide. They will produce this kind of structures, and they're called usually the dispersive shock waves. And in the resonator, so that's what I gave to you actually as a simulation file. So we see that basically this mechanism takes place more or less. So you can see that there is very first moment where you get this modulation due to the avoided mod crossing, so it's a background. And there is a transition when it's going to break, and due to the wave breaking, you generate this oscillating structure, and you get your large comb. So it's a pretty nice thing. So, and then we found out, like, so if you go and just go over, so that's what I did. As like I changed the detuning, like I increased the detuning here, I stopped, and I went back. So it's fully tunable. And I'm sorry for this like messy spectrum builds, but so what you see here, that there is a certain switching. So there are steps exactly like in Soliton story. And that was amazing discovery. And unfortunately, it was published before us by Weiner Group. we're like a few months late. But anyway, that's really nice dynamics, and I hope you learned how avoided mod crossings can be exploited and used in your research. Thank you. Okay, so let's bring questions to lunch. Please remember, write them down, because we really have to hurry. We are a bit out of.
We have time. I mean, they're taking the train at 2:54.
Oh, okay. So go.
Yeah. We're okay. Even the lab tours we can take.
Okay. So, Jeff, don't hesitate now.
Yes,
So.
please ask me questions. Too much wine last night?
I have one question. Like, I also saw that sometimes, to create more compliance, they use sideband generation.
The sideband generation. I mean, in which configuration once again?
Yeah, like what's so they use one Soliton and then they create two sidebands in order to have a more field spectrum.
In postpone? No, wait.
Yeah, I'm not so sure because I just read it.
No, but you mean you use the sideband in order to modulate your background and lock Soliton to a certain position. That's definitely a trick people use quite often, especially in lasers. I've seen a paper on laser stabilization due to this modulation of background. Actually, in LED, it works in a funny way. So you can have modulation of the background, and Soliton is going to be locked to this kind of position. Or you can have a plane wave, but modulated in phase, and you'll have some sort of effective potential. So you get constant as a modulus square, but the phase is non-trivial. Yes, so for example, sinusoidal, and your solitons will still trap to this kind of new potential, even if the intensity is constant. That's really nice tricks people often use. Yeah. Thanks. So okay, if there are no questions, let's move to the next speaker. Okay. You want a break? Because we're going to have a long 45 minutes lecture from Raphael after all. So it's planned to have four short lectures before break and 1 week after the break. It's okay for you? You still up to listen another nice story?
So morning everyone, I'll try to be brief. And so yeah, I'll be talking about phase modulated ring, but the main reason for the main interest of this system for me is nonlinear dynamics in so-called synthetic frequency dimensions. And first of all, what is it, synthetic frequency dimension? So I hope just the dimension is more or less clear for us, for you. You can imagine just a chain of atoms and dimension in real space. So synthetic dimension, it's almost the same thing, but in the case when you try to use internal degrees of freedom in your system. And one of the ways to create such a dimension is to take a resonance, a ring, and put a phase modulator here, and apply voltage on a frequency about 1 FSR or 2 FSR, so just a resonant modulation. So, and in fact, this system becomes equivalent to which one? This one. Yes, thank you. And in fact, this system becomes equivalent to such a chain, but not of atoms, but of rings that are coupled to each other with coupling strength J. And making an analogy to solid-state physics, there you probably know that direct space is our coordinate and reciprocal space is our wave number. Here, direct space is our frequency, and reciprocal space is time. And it becomes a pretty fascinating thing that you can measure band structure of such systems. So you can simulate crystals, but in photonic systems. And so in this paper, these 9 gentlemen, they found that indeed, if you apply voltage and you look at your field inside the resonator for different detunings, you can directly measure band structure of such crystals. For example, here they provide experimental results and simulations. On the x-axis, you can see coordinate of your ring, so it's just a ring, and on this axis you can see detuning, and so this line corresponds to your intensity inside your ring. They applied modulation at a frequency of 1 FSR, and they increased voltage, and they could see how they can create this dimension, and afterwards they applied more complex type of modulation, including modulation at 1 FSR and 3 FSR, and obtained this type of structure, and same for this. But what's going on if we have dispersion there and also nonlinearity? Because basically these results were obtained for a huge ring it was about 2 meters long, I guess. So there is no dispersion. And also it was, they applied quite low power. So there are some issues with powers because you have some losses in the part of phase modulation, but still, it was completely linear thing. What's going on if you have, first of all, dispersion? If you have dispersion, you don't have any more crystal, because you don't have translation symmetry in frequency dimension. And also, what's going to happen if you have not only coupling, if this nearest neighbor coupling which appears due to modulation, but you also have a chi3 in your resonator. So it means that you have four-way mixing, which we can't control, in fact. And so, using coupled modulation formalism, we successfully derived Lugiato-Lefever equation in this case. It appears that modulation leads to appearance to a potential in this equation. And so this equation becomes the Ginzburg-Landau equation or Gross-Pitoevsky equation. And particular thing here is that this potential breaks your translation symmetry. So, and what we may expect that now solitons may appear not in a random position, but in a predictable. And also, this system was studied for fiber loop cavities, which are described by complex Ginzburg-Landau equation, which is way more complex than LLE. And it was found that indeed phase modulation, it was found experimentally, that indeed phase modulation leads to appearance of such a cosine-like potential. And so, so you can see that this equation is quite complex, even more complex than LLE. And I would like to show you that one more time, simple, dispersionless, and time-independent analysis may give us important results. So, first of all, we renormalize it in Gorodetzky form. So you have seen it yesterday, and we consider dispersion. We neglect dispersion and time dependence, and we obtain equation on the intensity inside the field, inside the ring, and it appears that due to modulation, different parts of the rings appear to be at different branches of stability. So, for example, for given detuning, for example, normalized detuning equal to 5, this part of resonator appears to be at lower branch of stability, and these parts appear to be in bistable branch. And so, at least, and what if we provide a direct simulation of this equation, like we did yesterday, but with the potential, what we obtain? If we take anomalous dispersion, we can see that soliton exists almost exactly in this region of bistable branch. And using this fact, we can predict more or less the soliton existence range in modulated cavities. And so for different coupling strengths, we obtain that soliton existence range only shifts in the radiotuning region there. Also, one more interesting thing appears in my region. You can see that at some point your modulation stability becomes confined, and it doesn't go in the bistable region. We'll investigate later. And also, you can just change your sign of your dispersion in the equation, and you can try to simulate platicons, also called dark solitons, in this system. And it appears that due to this phase modulation, you have effective photon flux from your pump from your pump into sidebands, and you can generate platicons at relatively low powers, so like here. And also, we can predict more or less the Platikon existence range using just simple dispersionless analysis. Here you can see Soliton profile and its phase, and Platikon's profile and its phase. So it's pretty nice result, I suppose. Now let's take a look on chaotic dynamic. What's going on? So this picture was obtained when coupling strength was equal to 3, and it corresponds to more or less 150 megahertz. And here you can see special temporal diagram of chaotic state at different detunings. For example, this one corresponds to this detuning, and this one to this one. And you can see that, in fact, modulation stability in this system appears to be as just constant dynamics of creation and annihilation and collisions of solitons. It's more or less clear from this picture. But what's going on if we increase the coupling strength, so we increase the depth of our potential? This dynamics becomes more stable, in fact. And we'll see that we can obtain new stable states in this in this system. Also, one interesting thing appears if we set our parameters, our detuning and pump at a given position. And so you have seen that you cannot get Soliton just if you just launch your laser at some you launch your pump just at a given detuning. You need to start at blue detuned region and go through a my state, and then you can get Soliton. But imagine if you just put your parameters of your system in one point, and you'll just increase voltage of your on your phase modulator. So it appears that you can actually create Soliton in a given position, and you can see how it happens. This appears to the fact that your potential creates modulation of your background, and the position of this modulation is controllable by you. In fact, you can just change phase in your cosine. But if you continue to increase the voltage, you'll go into chaotic states, which you can also call Chimera states. So there are some works in optics about this, when you have coupled resonators. And for example, in this case, we have coupled resonators with two types of coupling: nearest neighbors coupling, which appears due to phase modulation, and also coupling, which appears due to full-wave mixing process. If you continue to increase the coupling strength, you'll get stable states. You'll just come from this point, just here. And these new stable states, you can see them in comparison with solitons. So in blue line, I show you just soliton profile, and in the red, profile of these new stable states, which can be considered as nonlinear structures in this nonlinear synthetic frequency dimension. Because in fact, since we have this stable structure, due to self-phase and cross-phase modulation, we achieve to get rid of dispersion. So these structures, they are dispersionless. And this system of high 3 resonator with high 2 modulator may help to simulate in real life nonlinearities in crystals, in one-dimensional crystals. Yeah. So, thank you for your attention.